Academy. Today we want to look at eigenvalues and eigenvectors. This is a linear algebra topic which is very crucial in linear algebra. It cuts across in both pure mathematics and applied mathematics. So let's follow and be able, if you have any question on either of the point, kindly leave a comment. I will be able to respond as quick as possible. If you have not subscribed yet, kindly subscribe. So let's look at polynomials or matrices. If you have this, we let that one be a polynomial and A be a square matrix, which is K by K, that means it's a square matrix. Then PR, the polynomial of the matrix, will be described as this: A subscript n power an plus that way to a naught times identity matrix. So AK is actually identity matrix, which is K by K matrix. If PR is 0, it will imply that then that particular matrix is a 0 or is a root of the polynomial. It's the root of the polynomial. Okay, let's look at an example. If we let A to be this matrix with ones on the upper triangular, let's find A to power K, that matrix A power K, for any positive integer K. So how do we get the power of a matrix? So this is generally what we are doing. So we try to do A squared, and we know A squared is actually A by A. No more cross multiplication matrix operation. So we'll get this. Then this one is A times A squared. We'll get this. That will imply, if you come up with this kind of relationship here, when K is 1, because generally AK will be equal to this 2, you can see 2 here is 2 here, meaning K here is K where? There. Then M, which is this bit here, this one, we see the relation between this and this, 3 and this. So you can see that's what you need to know. That's what you know. So when K is 1, M is 1. When K is 2, M is 3. When the K is 3, then M is 6. And when it's 4, then it is 10. So let's look at this relationship. What do we see here? We see that we can write K in terms of M in terms of K. And this relationship will be actually true. That will be actually true. Okay, let's look at another example. If you have this polynomial given like this, let's find that polynomial substitute of matrix A. So where we have been given A to be this. So already we have A being that. So what do you need to do? Where we have A, the highest power of our polynomial is power 2, is a square. So that means we will need also to have A squared. We need to have A squared. So that if you have to have A squared, it will mean that A squared will be given as in here. We are just operating that double multiplication, squaring A. Then we see that is becoming true. Okay, so that now writing our polynomial to a PR, this we are actually borrowing from our px, because it's equal to 3x squared minus 4x plus 5. So where we have x, we put a, and therefore we have this kind of polynomial here. So that from this polynomial here, we know the value of A squared, this matrix here, we know the matrix A, and we know the identity matrix. So we just substitute respectively. And then we open the brackets. So what happens after that? We are able to get the solution here. So this is actually what the question intends us to do. So if you are to find this PR, we will use the idea of the polynomial given. The polynomial given will give you to what power are you going to extend your matrix. So if it's to power 2, then you know you'll have to work to a squared, and then you substitute respectively. So when that happens, you have arrived to the answer. Let's take a remark. If px is any polynomial, PR is defined only for square matrix. So if px is any polynomial, then you know that for you to work out for PR, then you'll get it defined only if we have a square matrices. So that if you're having a transformation which maps V to V, which is actually a linear operator, then it will imply that PT exceeds where t to the power k will mean the t is k times, operating on t's k times, that's t to the power k. So having known that, having pointed that, it will imply that if you have px, which is x squared 3 that way, then pt, if you use pt for the operator, it will mean we need this maybe t squared plus t plus 4. So instead of using the way we were using matrices, we can also extend the knowledge to in the operation of operators. So in this case, our operator is t. So what we are going to do is actually substituting with the t. But we know t from the idea we have noted to power k implies t k times. So it means if it's t squared, then it will mean t 2 times, and as this becomes true. Remember, high V is the identity map of V to V, whereby if you have the identity matrix U, it will map it to itself U for all U's in V. That's generally the identity map. So having noted that, we can look at an example 3 here. Remember, so far if you have not clicked on the button down there for subscription, kindly just subscribe so that every time you can be able to refer most of the tutorials, and you can also get to know the ones which we are updating every week. So let this operator map this one to here, P2 to that, which we are saying there. This is what we are calling is a linear operator. It's a linear operator, as we have just noted from there. So what is happening, there is the combination of the way the operator is applying. Is getting the derivative of px first, and then adding p shift 1 x plus 1, and we have given if the function given is f ft is 40 squared minus ft plus 7, then you want to find the transformation of ft to px, where px is basically a quadratic expression. It's a quadratic expression. So what is happening here, we are taking ft, which generally we know that, introducing the operator t. This becomes true, okay? But from what we have noted, t squared is given by t squared t dot t, substitute respectively. Now we are having, our operation is having ft px. So that's basically what we are doing, ft fx, the operator. So for this one is the first part for operator tt. We transform. If you look keenly, this gives you this one for institution. Then we know this by the divination of the operator. It will do what? It will first differentiate. So that derivative of x squared is actually 2ax 2 minus 1, and therefore you have these 2x. Then bx, if you differentiate bx, you get b, because x becomes x power naught, which is automatically 1. It's automatically 1, and hence that. Then plus the shift. So after shifting, you just do it directly. While we have x, you substitute x plus 1, and therefore you have this. Expanding, this will be 2. Expanding, that will be 2. And the grouping. Remember, you group it in a way that it becomes the form of quadratic expression. It becomes in the form of quadratic expression. Now that we know ptt and we know t, we just do it direct now. So we substitute what we did for the first part, and you also do for the substitution of the other part, and clearly you'll see now the solution being that. Remember, if you have question on either of the part, just leave a comment and I will be able to look at it. If you have also a question that after I have this application, you can leave it, I look at it, and I will guide you now to arrive to the solution. Remember also to subscribe and share with your friends. Okay, let's look at another example. Suppose P is invertible matrix and fx is any polynomial. A matrix of same order as P, and we have A, which is a matrix of the same order as P. Then if you do the function direct, P inverse AP, and you do P inverse, then you first work for the function of A, P, you'll get, the two solutions will be same. If, for example, fx is given by this, then it will be like that fpap will be given by this. Wherever we have x, we are just substituting with P inverse AP, and hence we have this. Remember, we want to show this. We want to show that. Okay? We have introduced a polynomial fx, define as that. Then we want to take our left hand side and see what we want to show. Now next, we group FLAN will be composed of that, because these are p negative APs, or that repeatedly to n times, to n power. Same case for this is to n minus 1. Same to this is to n power 2. That's the reason you can see here we have 1 and a 2. This is n to power 1, so this you have only one composition. And this to power 0, and hence we have that. Because this basically is an identity. So having noted that, you'll see that P by inverse is automatically identity. So all that will reduce to this. Reduce to this. The AN, which is outside here, and the AN and the S here, because you are saying they will go to power n, then they will be to a power n. Then the last P is here, and the first P is here. And the same thing applies to n minus 1. So that happens to the last bit, and therefore, having if you check it like this, you see that you can group the P's, the n, which is the function operator, and to find that if you group them, they are inside that part, P inverse 1 or that, and then P, so that everything, all this, because this is FA, it is actually our required solution. It's our actual required solution. So having seen that, we have already shown that this relationship is actually true. You have seen that relationship is absolutely true. So if you have any question on either bits that we have tackled here, kindly leave a comment. Visit the other tutorials. They will also give you guidance on how we do this. Remember, this is mathematics and we all love maths.